Welcome to the Space Telescope Public Lecture Series, featuring tonight's talk, Armchair Astrophysics, Finding Physics Far and Wide by Quyen Hart of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers of the Office of Public Outreach. And I want to remind you that the Space Telescope Public Lecture Series will be online only for at least the rest of 2020. And because we are doing this online, we have to put special thanks out to our wonderful tech team, Thomas Marufu and Grant Justice, who are taking this stream and getting it to you to see live. Our upcoming talks next month in September, on September 1st, we have, well, a very long title, Sailing Across the Local Universe with Ulysses, a Hubble program to observe ultraviolet light from young stars by Will Fisher. And this is actually a very exciting program, one of the largest programs ever done with the Hubble Space Telescope. You're really going to want to see what that's about. In October, we will have a talk on the Nancy Grace Roman Space Telescope. This telescope was previously called WFIRST for Wide Field Infrared Space Telescope, and it was recently renamed to be the Nancy Grace Roman Space Telescope. They're having a conference here, or actually an online conference centered at the Space Telescope Science Institute in October, and one of the speakers from the conference will be presenting information on the Roman Space Telescope. And then in November, we have a really cool talk for you. It's called Astronify, Sonification of Astronomical Data. What if you could listen to the sounds of the universe, or the data of the universe, turn it into sounds? Scott Fleming and his team have worked on that with the Astronomical Archive at Space Telescope, and he'll tell you about that in November. You want to find out about this, you go to our Public Lecture Series webpage, stsci.edu/public-lectures. On it, you will see the links to our webcast, both on YouTube and on the STSCI webcast archive. And in the lower right, you can see the subscription button for the email. If you'd like to get reminders every month, you can subscribe by just entering your email address there. You can also find information about our upcoming talks. Each talk has its own page, and when you look at that page, you will find the description and the introductions, as well as the links to, after it's been archived, onto the STSCI webcasting page and where it is there on YouTube. Our email announcements, well, as I said, you can sign up at our website. And also, because we're doing this online and streaming to YouTube, you may want to subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. If you are a subscriber, you will get notices of our new videos, as well as reminders of these live events. Finally, if you have comments or questions about what you see here tonight, you can send them to publiclecture@stsci.edu. Our social media, we have social media for the Hubble Space Telescope, for the Webb Space Telescope, and for Space Telescope Science Institute. I'm sure we'll have social media for the Roman Space Telescope eventually. We're on Facebook, we're on Twitter, we're on YouTube and Instagram, and I myself I'll do a little bit on Facebook and Twitter if you'd like to know what I'm thinking. Now, news from the universe for August 2020. Our first story tonight, Saturn, again. Now, that sounds like I'm not terribly excited about this, but it really is exciting because we observe Saturn just about every year. Because as Saturn and Earth make their orbits around the sun, whenever Earth and Saturn come into conjunction, when they're at their closest point, we get a picture of Saturn. And this year, we got this image of Saturn. This is the 2020 image of Saturn from Hubble. And you got to think about this. This is the best picture we can get being here at Earth. If we aren't going to fly across the solar system and get there like the Cassini mission did, this is the best we can do. And this is a really great image of Saturn. Another cool thing about it is we can use ephemeris software to figure out where the moons are. And these white dots here, Are they stars? Are they moons? Well, we can figure them out. Actually, there are 5 different moons in this image. Enceladus, Epimetheus, Mimas, Helene, and Pandora that we're able to identify in the Hubble image. And you can see all the details of the wave bands that we use to observe Saturn. But I call this Saturn again because, well, if you're a follower of the public lecture series, you may notice that I do a picture of Saturn just about every year. Matter of fact, last year in 2019, I showed you this image. And then the year before that, in 2018, I showed you this image. And so we see Saturn just about every year as it passes through conjunction. And the point is that Saturn's year lasts for about 29.5 Earth years. So observing Saturn every year, it's really like looking at Earth every 2 weeks. And a season on Saturn lasts for 7.5 years. So every year is not that strong of a cadence in order to follow the developments on Saturn. And if you look at how it progresses from 2018 to 2019 to 2020, you can first see that the tilt of the rings changes, but look at the atmosphere and the banding structure and even the hexagon on the top. There are small but subtle changes every year in Saturn that astronomers are following using the Hubble Space Telescope. This is actually a program called OPAL, O-P-A-L, the Outer Planets Atmosphere Legacy Program. And it is one of the very important solar system programs that gets time on Hubble every year to follow how the changes in the large planets of our solar system. The second story for you tonight is planetary nebulae again. And what does that mean? Well, I think it means that I was a little lazy when I was writing the titles of my stories tonight, but it means we're going to talk about planetary nebulae. And the first planetary nebula we're going to talk about is NGC 7027. That doesn't have a pretty name, all right? But what is a planetary nebula first? It is a dying star. It is a medium-sized star. And when these stars die, they actually blow off their outer layers. And you can see the star at the center of this image, and that the material that has been blown off from the star is outside it, is being illuminated by the hot core of the star. This is a very young planetary nebula. It is just in the beginning stages of blowing off its outer layers. And this is what Hubble saw back in 1998 with an infrared instrument called NICMOS, the Near Infrared Camera Multi-Object Spectrograph. And we had also had an image in visible light from 1996. And back in 1998, we combined the two. And you got this really cool image of this dying star blowing off its outer layers. But these were the instruments that were used back in the late 1990s. Since then, we've had quite a few technical improvements on Hubble. So in 2020, we're able to take this image and transform it into this image. Ooh, this is really cool, right? I mean, you're seeing so much more detail with the improved instruments on Hubble. And it's not just that you're seeing higher resolution, which you are, but you're also seeing all the way from ultraviolet light to infrared light. This is a panchromatic image of NGC 7027. We're able to see details, and actually we're able to see changes in the structure. Because this is a young planetary nebula, this actually has changes in its structure over those 20 years. Well, there was another planetary nebula studied in this, and this one is NGC 6302, which actually does have a pretty more familiar name. Its familiar name was called the Bug Nebula. However, the Bug Nebula kind of got thrown by the wayside when we had the press release back in 2009 for this image, and we called it said it looked like a butterfly. So now everyone calls it the Butterfly Nebula. And this is just one of the gorgeous images from Servicing Mission 4 early release observations in 2009. This is another planetary nebula. But instead of having that shell structure, it's got this blowout structure that forms the wings of the butterfly, material flowing off in opposite directions, okay? And so this is actually a full high resolution image. And instead of getting higher resolution, what is interesting of the 2020 observation is that extra wavelength. So here is the panchromatic version of the butterfly nebula. Yeah, really gets a lot of really cool and interesting detail. And my favorite feature in this is actually something that shows up in the infrared. All right, and these arrows point to these splays that are coming off and make sort of an S shape across it. And that is ionized iron seen in infrared light. And it's the fact that it's just a sort of a jet of this ionized iron tells you something about the emission that's going on at the central star. Matter of fact, that tells you that there's probably a disk of material. So that's collimating this outflow into this jet, and perhaps that this disk of material is wobbling around, indicative that there may actually be two stars at the center, that this is a binary star that's helping to produce this collimated outflow that's sort of just wobbling to get that S shape as it spews out. So doing these panchromatic studies of these two planetary nebula, both of them pretty young planetary nebula, allows us to get more detail across more wavelengths, as well as to understand some of the changes over time of these very young planetary nebulae. Now we go to our, our featured speaker. Dr. Quyen Hart has been at the Space Telescope Science Institute as a colleague of mine in the Office of Public Outreach for just 1 year. I mean, it's kind of funky because I really think of her as, you know, an old friend now, but she's only been here a year. Previously, she was at the Regis University in Denver, where she was there for 10 years. She has an incredible history in teaching. She got her PhD at Colorado University in Boulder. And something unique amongst the astronomers I know, she was an atmospheric scientist at the Scripps Institute of Oceanography before that. So she's got a unique resume. And one really cool thing about her is that she likes to crochet, and she likes the stories of Winnie the Pooh. So she has crocheted a complete set of Pooh characters. Now that's kind of fun. Ladies and gentlemen, Dr. Quyen Hart.
Thank you. Can you hear me okay? All right. Thank you, Frank, for the introduction. I'm really, really happy to be able to talk to you all virtually tonight about astrophysics. When I taught university level physics courses, my students would say, physics is so hard. And I would say, well, you know what? My job is for you to change your mind about physics and your perceptions about physics, so that when you walk around, all you see is physics. And if you come to me saying, hey, I just saw this and I thought about physics, then I know that I've succeeded. So that's kind of the motivation for my talk tonight, is to have you see the connections of physics in your everyday life, to start to understand or understand more deeply the things that you might already be aware of. So what are we gonna do tonight? So I mentioned that I'm a firm believer that anybody can talk about science with anybody else. It's really in how you see the connections and what interests you and the people around you. Now, you might think that the science of astrophysics, you know, in this nutshell, is a really hard nut to crack, even if you're just starting to learn it. So you might wonder, how am I gonna talk about astrophysics if I don't understand it? And you wanna crack that nut open, right? So what are we gonna do today? Well, we're going to try to crack that nut open. And how are you going to do that? Well, you're going to need to use something that you're familiar with. And so what are you familiar with? You're familiar with your everyday experiences. So we're going to use some of those everyday experiences and draw the connections so you can understand some of the astrophysics, so that you can take your other your experiences to crack open this astrophysics nut here. So that's kind of the goal here for everyone. And once you do that, Then you'll be able to sit down and have a nice little conversation with the people around you, and who knows what, where that will lead you. Some interesting conversations, I'm sure. So I want you to think about this in a very beginning sense. Let's start with the beginning. What does physics mean to you? Okay. So you can look at all these images and say, oh yeah, I get that. I know what's going on there. I see a space shuttle going up in the sky, a roller coaster, I see a rainbow, I see light. So these are different phenomena that you see and experience in your everyday world. And physics plays some role in all of these. So physics is really the study of nature. It's the study of matter, motion, and the forces and energy that you see that allow the different reactions that you might see, phenomena that you might see. So then you might say, well, what is astrophysics? It's really simple. Astrophysics is the study of matter, motion, forces, and energy in space. Now, this is a very simple definition, but it encompasses some of the really basic ideas that we have here of what we're going to be learning today. So we're going to look at those everyday phenomena, not exactly what you saw in that previous slide there, okay, and use them to understand some of the basic physics principles to understand the terrestrial analogues out there in space. The laws of physics are universal, so we can apply our understanding of what we know here to what we know in space. And the universe is so large, of course, we have surprises all the time. So this doesn't mean that we can figure out everything, but we can figure out a lot with the laws of physics. So let's start with really something really simple. Okay, so Frank showed us all these wonderful images. We're seeing light. Okay, so the question down the line will be, well, where's that light coming from? How was it created? But I just want to talk about the really simple light and matter and how they can interact with each other. So a really basic concept here is that matter can emit light, like the hot filament of a light bulb. Matter can absorb light. So you should put some sunscreen on because you want the UV light of the sun to absorb by that material, but your skin can absorb that UV radiation from sunlight as well. When you look at sunlight through the window, the glass pane is transmitting light, so matter can let light pass through it. If you woke up and you brushed your teeth today, good. That means you saw yourself in the mirror and light was reflecting off that mirror, so matter can also reflect light. So when you're looking at all this, we're seeing that interaction. Now, when you look at sunlight on a nice sunny day, your eyes perceive it as mostly whitish light, right? But we know that on a nice, if it's sunny and there's some raindrops around, that we can get a rainbow. So we know that the sunlight is composed of the colors of the rainbow, but you need something to spread that light out. So on this diagram here on the left, this ray of white light here represents sunlight. And if it can pass through a rain droplet, that there's a little bit of transmission going on there, but the direction that each color of light takes is different depending on if it's red light or the blue light. On the inside of the rain droplet, there's some reflection going on. And then there's transmission through the other side of the rain droplet, and out the other side, you get the rainbow. And so that's something to spread out the sunlight into a rainbow is a water droplet here, actually many water droplets, so that you could see this beautiful rainbow that we saw a couple weeks ago in Maryland. Now you can do the same thing if you take a Blu-ray disc or a DVD player, DVD disc, and you hold it up to light, okay? You'll also get this rainbow effect because light in this case is reflecting off the DVD or Blu-ray, but there's tiny grooves in there that allow the light to reflect off in different directions depending on the color, which is why you see the beautiful colors here. So this is a something to spread out the sunlight colors into the colors of the rainbow, because the sunlight is composed of those many different colors. Our eyes just can't detect that. So if you go outside here, maybe you have a pot of zinnias like I do here in my yard. Maybe you have a beautiful bouquet of flowers or sunflowers here. So you can look at these flowers. I'm going to use this as an example here and start to think what's going on here. I just talked about light and matter and how they interact with each other. So what's going on here? Is it emission of light? Is it the absorption of light, transmission, or reflection of light? So you know that your eyes here are, you're seeing green, you're seeing yellow, you're seeing pink, you're seeing red, you're seeing this purple. So some light is getting into your eyes here, okay? And then it's going to the back of your eye and it's being absorbed by photosensitive cells in the back there that eventually send a chemical signal to your head and you sense light. Okay, so that's what's going on biologically. Now you probably have a really good sense that the flowers are not emitting their own light, because if you were in complete darkness, you know you can't see these flowers, so you know that's probably not emitting light. You probably have a sense that they're not really transmitting light, because if they were transmitting light, you would need something underneath the flowers, like, you know, hidden in these leaves here, to shine through it for you to see it. That's not what you see. So that leaves us with either there's some reflection going on or some absorption going on, right? So whatever's happening here, like in the yellow of the sunflower, it's a yellow light is getting to your eye for you to see the yellow part, okay? And the green part of the leaf here, something is happening where the green light is coming to your eye. So really what is happening here is that there's pigmentation in the flower petals. There's pigmentation in the green leaf. Now, when I say pigmentation, what I'm really saying is a molecule. There's a molecule that's very specific to that particular flower petal. And it's specifically, for the case of the yellow sunflower here, that pigmentation preferentially absorbs every color except yellow. And yellow is reflected towards our eye. So it absorbs the sunlight, but preferentially reflects the yellow. So when you see green leaves, the pigmentation in the leaf, again, it's a molecule here, absorbs all the colors of the sunlight except for the green, and it reflects. So this is a case of reflected light and absorbed light at the same time here. And if you take a close-up look of flower petals, you can start to see that there's special distributions of this pigmentation on the flower. So these are cutaways of flower petals. Sometimes that pigmentation is all throughout the material. Sometimes that pigmentation is just on the outer edges of the petal here. And sometimes it's only on the edge. But the fact that we see red or we see purple is the fact that that petal did not absorb that particular color and reflected it out, okay? So and that's what we perceive as color. So now you get a sense of what color means, okay? So now we can say, oh, Frank showed us this picture of Saturn. What does that mean? Instead of showing Saturn, I'm going to show something else. I'm going to show you some Voyager 2 images of Uranus on the left and Neptune on the right. And they both have this beautiful blue hue to it. So what's going on here is that in the visible light, these planets do not create their own light, but we see them in visible light. And that's because sunlight is shining on their atmospheres. And the upper layer has methane gas that preferentially absorbs more of the reddish colored light here. And so more of the blue light makes it down towards the methane clouds, which then reflected back out into space, which was captured by the Voyager cameras for us to see here. And so there's a lot of absorption going on here and reflection to be able to give you that hue. So that hue is very indicative of what the atmosphere is made of. Now let's take a look at Jupiter, because Jupiter has some more interesting patterns to it. So there are a lot of zones and belts here. And these are ammonia clouds. The white here are the ammonia clouds that are higher level clouds. And the darker areas here are deeper clouds in the atmosphere made of, you see here, another kind of a ammonium compound. Now Jupiter rotates very, very quickly, and that's partly why it has a very unique banded structure. And we also have the great red spot here. So here's just a nice video of what's going on. So again, in the visible light, this is an interaction of the sunlight with the chemical composition of these trace elements of ammonia and that's absorbing preferentially all the colors except red in the case for this banded structure here. On the other hand, these white ammonia clouds, they look white to us. So a lot of almost all the colors in the visible spectrum from the sunlight is reflected off there. And this red color here is also related to, and the great red spot is related to the chemical composition of what's going on there, doing a combination of absorption of all the different colors in the rainbow, but reflecting out the red. Okay. See there, stop that. So now we can take that and just go out a little bit further into space here. That's just kind of like in our backyard. So now let's take a look at a really fun cluster that you can definitely see with your eyes, called the Pleiades star cluster. Sometimes it's referred to as the Seven Sisters. It's near the Orion constellation. And so what you see here are the stars, which are these brightest objects here. And you can see the diffraction gratings, these spiky things, part of the detector here. But then you see this bluish glow everywhere. Okay. So what's going on here is that there's a lot of dust. In fact, that dust is in the foreground, in between us and those stars. And the dust grains easily scatter, which is a special kind of reflection, scatter the blue light of those young stars. It preferentially does that. And so we call this a reflection nebula, because the light is being reflected or scattered away in the direction of our eyes for this telescope or your eyes to see it. So this is an example, again, of light interacting with matter in a very, one of those four ways. In this way, it's a reflection here. So that's an example of how we look at light in a slightly different way that you might not have thought about before. Now think about something else. So you've been listening to my voice, so it's sound, right? So maybe you've been lucky or unlucky to have a recorder by a little kid at home. Maybe you have that sound going on in your head. If I was physically at the Space Telescope right now, you'd hear my voice. But as we're doing everything virtually here, you're hearing my voice through a speaker. And so you hear me. The sound here is being carried through the air from whether, well, for everybody here, it's through your speaker or your earphones, whatever you're listening to. And it's traveling through the air, and then it hits your ear, it travels into your ear, vibrates some bones, and eventually you get a chemical signal that sends an electrical signal to your head, and you hear sound here. Okay. So what needs to happen for sound, though, is that it really, what it is it's a wave, and this wave has to move through something. So on your speakers there, if you look at it, if you uncover it, you should see a speaker that vibrates up and down, okay? So as it vibrates up and down here, it can cause the air molecules to compress together and rarefy or spread out. So if you look at this image here on the screen, you can see that where it looks like it's ring-like, that's where the air molecules are closer together, where it's compressed. And where the air molecules are a little bit further apart, that's where it's rarefied. And if you look at that, the rings are kind of separated by the same amount. So there is a unique signature for this particular sound wave that is being displayed here. And those little dots there represent the air molecules. So another way to represent this is, imagine if I were to take a snapshot, I'd see molecules compressed here, which would be an increased air pressure. But then when it's rarefied, it'd be decreased. And so you get this alternating compressed air, rarefied air, compressed air, rarefied air, compressed air. And that whole wave moves out from the source, okay, and propagates through the air. So we can talk about the characteristics of this wave. This wave has a speed. It has to move through the air at a certain speed. There's a directional component to it. There's a wavelength as well. And if you know wavelength and you know speed, then you can talk about the frequency. So when you're singing a song, you might sing at a C note. So the C note is a certain frequency, and that corresponds to a very particular wavelength of a sound wave through air. Now you might say, okay, I get that. Now, if you ever go into a nice empty room and you talk, you'll find that you'll get a lot of echoes. It's pretty fun to just sit there and say, hello, 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 right? So we've got a person here making that hello sound, and the sound wave leaves and then can hit a solid object and reflect off of that. So now we have sound waves reflecting off something solid, and this is what we call an echo. Okay. Now this happens with radio water waves as well. So this is an image where you can see shadows of water waves in a pool, but it hits a wall here and gets reflected. So waves here, again, have a speed. If it's moving through air, it has a certain speed, sound wave. Sound can also travel through water and can travel through solid substances, but they will travel at different speeds and wavelength and frequency. And there's energy associated with that. Okay, great. So we know that waves have these characteristics. They can move, they have a wavelength, and they can reflect off things. Well, guess what? Light is a wave, okay? Light can be a particle too. I won't get into the duality of light here, but I want to talk about light as a wave. So light is a wave that moves with a speed of 300,000 kilometers per second here, which is about 671 million miles per hour. So really, really fast. Light from the sun takes just about 8 minutes to get from the sun to us traveling at the speed of light. So that's really, really fast. Now, different colors of light have different wavelengths and they have different energies associated with it. But all the colors of sunlight here travel through space at the exact same speed. So that's different than sound waves in that sense that they have the same speed. There's a speed limit in the universe. It's 300,000 kilometers per second. So we know that light can reflect. We've already talked about how light can reflect off of mirrors. Now, if you have a laser is a very specific color of light. In this case that you see on the screen is a green color here. And you can use multiple mirrors in an optics lab for, and bounce it around so we know it can reflect. If you are cleaning perhaps and you stir up a lot of dust, you know that the dust can also reflect off of, the light can also reflect off the dust. So we know light does this, and we can describe it mathematically as a wave that reflects and interacts with light and can reflect in this way. So can we see light echoes in space? Something like the sound echo, but a light echo, and sure enough we do. So if you have a dusty environment around something that could give a burst. So when I do like a click or snap my fingers, that's a very sudden sound, right? So if I do a clicking sound, you can wait for it to hear and bounce off things, and you can start to figure out the distances to things, okay? So animals are able to do this. Now, if in space we have something that does a burst of light and let it emanate away, it could also reflect. So let me start this video here. So this is V838 Monocerotis. It is a star that underwent an outburst in May 2002. So what you see here is the light reflecting off dust that was already there. But the light had to travel outwards to hit those dust particles and then reach the Earth in the telescope here. So the star that went outburst is at the center. It became very red here. It underwent a burst of light, an outburst, restart it, and it illuminated the dust. Now, all this dust exists out here. You can't see it yet because the light hadn't reached it yet, but we know what the speed of light is, and we can watch this unfold with these Hubble Space Telescope images. And because of that, we can get the distance to this object. And this object is 20,000 light years away from the Earth. And that's a geometrical distance estimate, which is pretty cool using a light echo off of dust from a star here. So that's an example of a light echo. Now this is nearby. This is in our own galaxy. What about a little bit further away? So we have a star-bursting galaxy. So a star-bursting galaxy is a galaxy that's creating stars way more than the Milky Way galaxy is doing. And in fact, it's so much that it's actually blowing material out of this spiral galaxy here. But what was really interesting is in 2014, a supernova explosion went off, and that is an end to a very massive star's life. And supernova explosions are very energetic. And again, a burst of light that can come out. And so what we see here is when that supernova went off, this was embedded in a very dusty area. And so we see a light echo here as well. And so this is unfolding over 2014 all the way to 2017 there. So over the course of several years here, seeing that light echo. And that light echo is not exactly symmetric. So the fact that it's has brightening in certain areas actually gives us more of a information about how the dust is distributed in the region around the supernova explosion. And then if you look at the reflection, this light echo, in more than one wavelength, it gives you information about the dust itself, because dust interacts with light differently at different wavelengths. And so if I look at it in one color and then look at it in another color and then another color, that gives me dust properties, which is pretty cool from a light echo. Okay. So it's just light bouncing off something instead of sound waves. All right, let's talk about some more light, because it's, you know, I've got this fireworky looking background behind me, which is a Carina Nebula. So who doesn't love a really good fireworks show, right? So I know a lot of people's 4th of July celebrations were derailed this year. My neighbors had a really nice fireworks show. So this is me sitting outside of my porch watching fireworks. So it was quite lovely. And it looks a little bit yellowy in color, but you know, your past experiences, you've seen fireworks of many different colors, blues and yellows and reds and greens. And so what you're seeing here is there's an emission, something is emitting light, and it's by some chemicals that are in the fireworks themselves. So there's a combustion that inserts energy, and then you get this light. So the question is, why does it have those specific colors? That's really what we're at here. Okay. So when you're looking at certain colors of fireworks, it's actually due to the chemical composition of the salts or the powders that are composed, that are in the firework here. So for example, if you see yellowy colored fireworks, it's most likely sodium. If you see some pink, that's lithium here. Green is barium. We've got some potassium that's a little bit more kind of tingy, like yellowy pink, and copper is a little bit more bluish green here. So you might remember when you were in chemistry class in high school that you used to do a flame test as one of your experiments. You swish around a metal rod and you put in a solution and you stick it over the flame, and the flame that you would see there is it's because it's heated up. That solution got heated up, but it only displays certain colors. Hence the flame test there. So what's really going on in order for us to see this light? Okay, we have to talk about the atoms themselves. Okay, so let me take sodium, the sodium atom. So the sodium atom here has, to make it a sodium atom, the nucleus of the atom has 11 protons. That makes that sodium. There's also some neutrons in there. And then if you want, those protons are positively charged. So if you have a neutral sodium atom, then you have to balance the positive charges with the negative charges, which are these electrons. And so this cartoon of an atom here just represents kind of the energy states that those electrons can be at. So there's a configuration that sodium normally wants to be at with those electrons. Now, if you add energy to that atom, you can change the configuration, and you can actually get one of these electrons to go to a different level, to a higher level. And to go to a higher level, you need to gain energy to do that, because it takes work to do that. So if an electron can gain energy, it's great. It's like, yay, I gained energy. But it doesn't like to be in this higher energy level. So it's going to be like, I'm going to go down. And in the process of going down back to a lower energy state, it emits light, okay, to do that. And it's not just any old light. It's a very specific color of light. Now, you might be thinking, okay, I've learned this before. I remember hearing about it. This is really quantum mechanics here, because the energy that the electrons can give off is dictated by the state of this atom here, which is dictated by quantum mechanics. So really, when you're looking at fireworks, there's quantum mechanics going on here. So that's really deep for your for today's armchair astrophysics there. All the atoms are different. So if I go back to sodium, there is, for the temperatures of combustion, there's a very unique transition that electrons will make that will predominantly give off yellow light. And that's what you see here. Now, if you look at street lights, some of the older street lights around, some of those street lights, if they have not switched out to LED lights, are yellow. They're yellow because there's a sodium gas inside. And that sodium gas is heated by electricity, and it gets those electrons excited, but then they give them some energy, but then it gives back the energy in the form of light. So yellow streetlights are sodium. It's the emission of light by atoms. When you see neon signs, it's the same idea, except they're not always filled with neon. If it's really, really red, then that tube is most likely filled with neon. And to heat the gas up, you put electrical charge through it, and that allows the electrons to go to higher energy states. And then when they always go back down, they emit that color of light. And so all these different colors of neon lights actually don't always contain neon, and it has to do with the atom. So sodium here produces that yellow light, but because helium is different than neon, it has a different color. Because argon is different than neon from an atomic level, it produces light that is different than neon. And it has to do with that atom. That atom itself is really key. So now you understand firework, the chemistry of fire. This is really chemistry, but it is at the heart of it physics. Okay. So now we've talked about terrestrial fireworks. Let's talk about cosmic fireworks now. So here's the beautiful Lagoon Nebula. And this is an emission nebula in space. So if it's an emission nebula, there's emission of light here. So this emission nebula is a place where many, many stars are born. And in visible light, you can see one of the stars at the center here, but there are many more that are hidden behind here, this cloud of dark dust. So let's just look at the colors first. The red hue here is showing us that the nitrogen gas has been, the electrons have gained some energy, and when they release that energy, we see this red light that nitrogen gas is giving off, and it's getting heated by those embedded stars at the center of that nebula. The green hue is from hydrogen gas. It's really, really easy to excite hydrogen when you look at normal everyday stars like this. The purpley hue here is a combination of hydrogen gas, oxygen, and nitrogen. So the fact that we see this light emitted by different elements is how we know that those elements are there. Now, you can't see color everywhere. In fact, some of the gas and dust here is so dense that it doesn't even let the light from behind it to go through it. Okay, so there's no transmission if the density here is very high. And so these dark clouds that you see here are just really, 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 really dense dust clouds. Dense for space, maybe not so dense on Earth, but dense for space for sure. That's an example of cosmic fireworks in the Lagoon Nebula. This year, Hubble celebrated the 30th anniversary, and we had this beautiful image that we also called the cosmic reef. And there's actually two NGC catalog objects here, NGC 2020, which is actually one very massive star that's puffed off its outer atmosphere. And the hot light, so the energetic light of that star is heating up the gas that it's been puffing off. And that is mostly oxygen that's showing up in the blue here. There's a whole bunch of young stars that are being formed in here as well. Some of them are 10 times the mass of the sun. They've recently formed, and they're the sources of energy that provide the atoms with energy to gain some energy in the electrons, so that when they fall back down, it gives off this signature. And the hue here, the red is from hydrogen and nitrogen again, and blue is oxygen. So some more cosmic fireworks. And it's a glowing star formation region. And we see lots of this out in space, lots of different regions that are emitting light from very specific atoms, not too dissimilar from how the light from fireworks work. Okay, so we got light, we've got sound, we've got fireworks. So let's move to air. Let's move to wind. Okay, so on Earth, like today in Maryland, it was really windy and rainy. And what is wind? Wind is just simply moving air. That's all it is. So if you want to go fly a kite, the best wind values to go, the best breeze here is 5 to 10 miles per hour to fly a kite. The other day, it was just a nice breezy day in my backyard, and breezy winds are about 15 to 25. And then we know that we can get quite extreme gusts of wind for very hurricane-like weather here. So Category 1 hurricanes have sustained winds of 74 to 95 miles per hour. So wind is just moving air. That's it. You got wind is air particles moving, but they have to move somehow, right? So how do you move something? How do you move matter? How do you accelerate matter? Well, Newton, this is the only equation I promise you that I'll show today. F equals ma. So to cause something to move from rest to some velocity, you have to apply a force. So if wind is moving, it wasn't breezy, then all of a sudden it was breezy, there must have been a force to move that air along. So we need a force. That's very important. Now, take a very ideal situation where there's no wind at all. It's a very still day, okay? So maybe if we think about this column of air here, just due to the gravity of the mass of the Earth here, if you're standing right here at the bottom of this column of air, you feel air pressure because it's just the weight of all the air molecules on top of you. And you know that if you go to higher elevations like Denver, for example, the air pressure is a little bit lower because you're now standing 1 mile above sea level. So the air pressure is a little bit lower because not the same number of atoms are pushing down on you. Now, this is where nothing is moving. There's no, it's still, there's no force yet to cause air to move around, but we know air moves around. Why? Okay, well, air needs to move around on Earth when it moves from an area of high pressure to low pressure. So you might say, well, what's that? What's high pressure and low pressure? It's very, very simple. So here we take sunlight, and sunlight hits the surface of the Earth and it warms the air near the surface, okay? So hot air, temperature is really just the motion of particles. So if you heat air up, the particles are going to move around faster and it'll become lower density. Whereas colder air won't move around as much and it's just, it's denser air. So if you heat the air up, it becomes less dense. And what does less dense air want to do? It rises. And so the warm air rises. And what happens is that it leaves behind a low pressure from where it just was. So what happens is that high pressure over here will flow towards the low pressure where the warm air just was. And that's wind. And the bigger the difference between the pressure at the ground and the pressure nearby, the stronger the wind. So you can have very gentle breezes, or you can have a really gusty breeze where there's major differences in pressure. So that pressure change is what is the force that allows the air to move, okay? Now we know that wind can push you around, okay? It can push, we can have this windsock and we know the direction of the wind. It can sculpt trees. It can sculpt the Earth. It can actually push particles away. There's erosion. So wind erosion is a real thing. So this rock formation here is wind erosion. Now, this is air physically moving around. But what if you're physically moving around? You can feel a wind, right? So if you're moving through the air, it can feel windy to you, even though it's not actually windy because you're moving through the material. So if you put your hand outside your car, you know that your hand moves backwards because of the force of the wind as your hand moves through it. So there are many windy scenarios in the universe. And let's start with some really basic one, maybe something that you've already seen before. Now the sun gives off a wind. Okay, so there are two, let's talk about the solar wind. The solar wind is actually composed of fast moving particles. Now, not particles like the air molecules on Earth, but very energetic charged particles, but it's a substance. And they're fast moving too. This solar wind can move at about 1 million miles per hour. And that wind is going off in all directions in space from the sun. Now, a comet here gets its very beautiful appearance when it approaches the sun. Now, a comet really is just a ball of ice with a lot of dust and rocks in it. So it's a dirty snowball. And it's cold when it's out far away from the sun. But when it gets closer to the sun's radiation can start to heat it up. And then the solar wind can affect the material that is that's getting heated up in the comet itself. So this is an image of comet Neowise that you might have heard about being visible earlier this month. Comets usually have two tails, And the comet itself is quite small. It's only on the order of a few miles or so, but it's usually icy, like I said. So if it gets too close to the sun's radiation will start to melt it. And it actually can also excite and heat up some of the molecules so that their electrons can go to higher energy levels where they don't want to stay, and they'll de-excite and they'll emit light. So what you see here is called an ion tail, which is a gaseous tail from heated molecular gas, specifically CO2 and N2, molecular compounds that you're familiar with here. So it's carbon monoxide, carbon dioxide, and molecular nitrogen, which is most of the composition of the Earth's atmosphere, in fact. And it gives off this bluish hue. And it points roughly in a direction away from the sun. Now, this tail is created by the sunlight interacting with the molecules. This whitish tail, now you can imagine, oh, it's really white. It must be doing either emitting all the colors or reflecting all the colors. That's the dust tail. And sunlight is reflecting off of that dust tail. And the solar wind, the particles from the sun, that solar wind, are pushing the dust particles away into this beautiful tail. So that tail also always points away from the sun because it's a result of the interaction of the wind with the dust particles themselves. So really, what is a comet? Comets are nature's windsocks. It gives you a directional component, and it can give you something about the energy associated with the solar wind when you look at a comet. Now, there are other features that are very large in the universe. So for example, if you take an elliptical galaxy is a collection of older stars older than the sun is. And this could be hundreds of billions of stars. And in the optical, it would be this yellow light here. Now, if there's a supermassive black hole at the center that happens to be very active, it can shoot off these jets that we can see with emission in radio light. And so this false color red is a jet that's ending in the material around this galaxy. And this is really big. It's a big feature. It's 1.5 million light years wide here. So the question is, what will happen if this is moving through space, let's say in that direction, okay? And what if it was moving through some dense material? What do you think might happen? Could that happen? Where you feel a wind, even though there's not a wind, it's because you're moving. So galaxies sometimes collect in clusters of galaxies. So in this image here, each little yellow blob is an elliptical galaxy. Immersed in all, this is in a very dense gas that happens to be really, really hot. So hot that it emits X-rays. You can't see it invisible, but if I switch to an X-ray telescope, it's really, really hot there. This gas is emitting, this gas is 10 million degrees Kelvin, and it's really dense. So imagine I take that galaxy, and let's say it's in that cluster, embedded in this gas, and it's moving, okay? Something's gonna happen to those jets and those lobes in that radio source, something like that. And we see evidence of that. They're actually called bent radio galaxies. It's kind of like having your hair swept back if it's a really windy day here. Or you can think about it as a wake of the jets as the galaxy moves to that hot cluster gas. And so the galaxy is actually at the center here, and this is one of those, the jets here, and the lobes are a little bit shredded, but it's bent back, hence the bent jet name here. If you take a survey of lots of different radio galaxies, you can start to see that they're not all straight like that Hercules A image. Some of them are bent back like this. So astronomers look for bent radio galaxies because it's an indication that it's moving through something dense. And most likely it's in a dense environment, which means we can find clusters that way. Sometimes it's easier to find a cluster by finding one object and looking for them in the vicinity around that. So that's one way that astronomers do that. So that's another windy scenario that we can see out in space. Another windy scenario is very similar to the erosion of rocks by a wind here on Earth. This is the young star cluster NGC 602. There's a bunch of young stars here that are very, very massive, pumping out a lot of radiation. And that radiation, we call it a stellar wind. That wind can sculpt the gas around it. And you can see these beautiful ridges here. You can see that it's lit up because that young star cluster has heated the gas to create the light we see, but it's also carving out the gas as well. All right, so those are some windy scenarios here that we see out in space, that kind of analogs to the windy scenarios we see here on Earth. Now let's talk about spiral galaxies. When I first started my PhD, someone had asked me, why do you want to work with spiral galaxies? And the first thing that I blurted out of my mouth was, they're beautiful, because they are. So I could stare at these all day long. And one of the things about spiral galaxies is that spiral nature. And we see something very similar across all these galaxies. They have these arms that are easy to see, okay? They also look bluish in color, okay? They also appear, there's these dark dust lanes. The middle of these galaxies are more yellowy in color. So all that gives us clues to the formation history, but I really want to concentrate on the spiral arms here. Now, galaxies are collections of hundreds of billions of stars, and they're all moving. And we can watch these stars move, and we know that the stars closer to the center move around faster than the stars further out. That's something that we've known when we even look at our own galaxy here. So the question is, these galaxies have been around a long time, and we see these spiral arms. How do they persist? Okay. So here's an example of the pinwheel galaxy. The question might be, maybe it's just because it's rotating. That's why I see spiral arms. Now, there's a problem there. If I just put all the stars into motion and say that the spiral arms here, so this is a simulation, that the stars that are in the spiral arms are always in the spiral arms. That's my assumption, are the same stars always in the arms, and then I let them move. So remember, the inner stars here go around faster than the outer stars. So what's going to happen is that over time, the spiral arms are going to wind themselves up so that they eventually disappear. So this can't be what's happening because we see a lot of spiral arms in spiral galaxies. We don't see them in this scenario. So this is not what's going on. This is a winding problem if we assume that the stars are always the same stars in the spiral arms. So there must be a different reason for why that's happening. So let's switch and think about traffic jams. I'm sure we've all been in a traffic jam one time in our life. One thing that's common with traffic jams is that there's always a high density of moving cars. Now, you eventually get out of the traffic jam. Sometimes you don't know what's happening to cause the jam, but your assumption is that it was going fine until somebody did something like that red car and everyone slowed down. And as a result of that slowdown, a wave of slowness starts to move back down the highway, okay? So I'll play it one more time. So everything's going fine, then a disturbance happens, that car, and it causes cars to slow down. And as a result, everyone needs to react to that. And so this is a density wave of a traffic jam that can move along at a different velocity than the cars that are there. And cars can move through that area of higher density, but that density might stay there and it could persist there for a long time. Now imagine I take this roadway and turn it into a circle and have traffic go. So if you take a look at the circle here, you can see that the cars are moving around in an orbit, and the area of density also moves, but it moves at a different pace than the cars that are in there. So we can talk about the density wave that moves around in the galaxy at a different pace than the stars. So this concept of a density wave, which is basically like a traffic jam here, has been explored to try to understand spiral arms. And indeed allows us to understand the nature of spiral arms, that it's really a wave of density that when a star enters that area of higher density, it gravitationally is attracted to that spiral arm and then it exits out the other side. Now, if you're a cloud of gas, when you enter the spiral arms, you get compressed. And if cloud compresses, it heats up. If it heats up, it can form stars. And this is why there's a lot of star formation going on in the spiral arms, because they're areas of higher density, like the traffic jam. And when you get a lot of dust and gas, you can get star formation. And that's also why they're very blue, because the youngest stars are blue and they don't live for very long. So they're pretty much where they were born. And that's why we can see the spiral arms so well because of that. So spiral arms are just really cosmic traffic jams for stars and gas. And we can use some of the same physics to try to understand that. All right. The last thing here are bubbles, blowing bubbles. So this is a favorite pastime of mine, to sit down and try to get little bubbles, big bubbles, bubbles that have a very pretty iridescent color. I won't get into the color, but the idea here is that when you're blowing bubbles, you need to have something inflate the bubble. And in this case, it's the air out of your lungs. And the material here is the soapy mixture. And there's some amazing physics that's going on here. But the key takeaway here is that you need something to inflate it. Soap bubbles need to be inflated. So let's look at some bubbles in space that are inflated, not by wind coming from your mouth, but by radiation. So we have these blowing bubbles in space. So on the left here is the Bubble Nebula. The Bubble Nebula is an emission nebula. It's about 7,000 light years away. It's about 7 light years across. And there's a very hot star at the center here that's giving off a very strong stellar wind, not different from the sun's, but much more powerful. So instead of 1,000,000 miles per hour, this wind's going out 4 million miles per hour. So really, really fast. And that wind slams into the surrounding material, and it's kind of like a snow plow, and it piles up some of the gas there, creating this structure, this rim here. And that hot star is pumping out a lot of high energy light, like ultraviolet light, and it heats up the gas. And that's the source of energy to light it up as the emission nebula. So the green here is hydrogen, the blue is oxygen atoms, where the electrons have been gained some energy to go to some higher energies, but then they go back to lower energies, emitting the light that we see here. On the right here, we see a supernova remnant. So this is a quick, very powerful explosion. And in that powerful explosion, a lot of radiation and mechanical energy is imparted into the surrounding region. And this is most likely some of that material that the star, which is no longer there, left behind, but the material collides with each other and can create this emission of light here that we're seeing. We also have stars that are quite massive and undergo outbursts. And that outburst here create these double lobe structures. There's probably 2 stars here in the image on the left, Eta Carina. And it's embedded in nitrogen gas that's glowing here in red. In the ultraviolet, there's magnesium. And these 2 lobes here are dusty lobes. They're quite thin, but they've been puffed up by the outburst. And because there's a disk of material, there's a kind of a bottleneck at the center here. And the really cool thing of this image is that there are holes in the dust of those lobes. And so you can see streaks of light coming out through those holes here. But this is another example of blowing bubbles in space. Now, these are all quite small, small being solar system size or a little bit bigger, at least for Eta Carina. On a very large scale, we have the Milky Way galaxy. So imagine I could stretch it out. This is the Milky Way galaxy. See an edge on from edge to edge. It's about 100,000 light years in diameter. We have a supermassive black hole. It's not active right now, but we think that it was active in the past because we see these 2 lobes of extremely energetic light from gamma rays, even more energetic than X-ray light. And we see these lobes, these bubbles being blown above and below the disk of the Milky Way. And we think that in the past, the supernova was, sorry, not the supernova, the supermassive black hole at the center of the Milky Way had a lot of material dump on it. And this is kind of like a cosmic burp where the material comes out. But it was very energetic to emit these gamma rays here. But again, blowing bubbles in our own Milky Way. So these are just all different examples of common everyday things that you see around you with some basic physics, and we can use that to understand what we see in the universe. And as we go through this, I could redo this whole talk and talk about different physics and all that. So this is a starting point for our journey for armchair astrophysics. The world around you is beautiful. And Frank just showed at the beginning here, the butterfly nebula. And beauty is in the eye of the beholder. So for you, maybe it's in these images that we see, these beautiful emission nebula and spiral galaxies or supernova remnants or planets. It could be many different things. Maybe the beauty is knowing that we're here on the Earth, we can't go anywhere, yet we know so much because we let the light from the universe come to us, and it hits our detectors on our telescope. It allows us to be in a virtual starship where the light comes to us or to your eyes, and that light came from a star, came from the gas around the star, and traveled all through space, entered your eye, and disappeared. So I personally think that's beautiful when you think that you touch the universe. And that's one way, is through the light, because light is a cosmic messenger. Maybe you think that the beauty in the universe lies in the fact that there is all this underlying physics, and you can use mathematics to understand that. All of these here lets you think about what the universe, the world means to you. Sit down with a friend, have a conversation about what is stirring your curiosity. Okay, so make sure you have that really comfortable armchair, because you might have a really long conversation, and even better, take it outside and look up. Thank you.
Thank you, Quinn. That was wonderful. I was waiting for you to, when you were talking about supernova, to get into the snowplow phase of the supernova blast wave, right? I thought that would be a funny way to pull things in.
Yeah.
But been watching the conversation on YouTube. We've got lively conversation in behind here, and I only was able to glance at it, but Grant has been following it better. So let me bring in Grant Justice, who is our behind the scenes tech guy who's been following the chat. And Grant, do we have some questions for our speaker?
We do. And the first one, you've answered one of these, but I'm going to bring it up again because I want to see how Quinn answers it, just to give the audience both viewpoints. So if light is a particle and all particles have antiparticles, does light have corresponding antiparticles? This is one of the first ones I saw in the chat.
I'm going to have to pass because I don't have that at the tip of my tongue. Frank, do you have an answer for that?
All right. Well, the answer is that the photon is its own antiparticle. Okay. The photon has no mass and no charge. So if you try and make the opposite of that, it's the same thing. So the photon is considered to be its own antiparticle.
Thanks, Frank.
Okay. Yeah. All right. And when referring to the differences in energy of particles, what is an analogy for us to use to understand what energy is? What's your go-to, or what's one that you think would be useful for the audience if they're trying to explain to someone?
Ooh, okay, well, that's a great question. Well, energy, that word is all encompassing. We have different kinds of energy. So in today's talk, light is one of those forms of energy. So I can talk about red light. It carries energy. Specifically, I'll categorize it as radiative energy, energy carried by light. Now there's energy that's bound up in atoms. For example, molecules, in order to break their bonds, you need to give it energy in order to break those bonds. So we can talk about the bonds that hold atoms together. We can talk about the energy that holds molecules together. There's gravitational energy, potential energy. So energy to me is something that can, either it could be part of a characteristic of the particle. If it's moving, it has kinetic energy. So that's a characteristic of what it's doing. So that's matter, motion, and energy combined together. That's what I was talking about with physics there. If we're talking about just a particle sitting, like you sitting on your chair, I could talk about all the energy associated with you just sitting on your chair. So it's bound to the situation, is another way to think about it. With atoms, there's energy to keep those electrons bound to those atoms. So if you want to change that, you have to give it energy. And if it wants to change back, it has to give off energy. That energy could be light, but it could also be through a collision, because collisions also have energy associated with it as well. So there's in astrophysics, we have emission of light that can be due to collisions when it's really, really low density. But it has, in physics, energy has a unit associated with it. So,
You know, Quinn, I always find that people have trouble with potential energy, right? Because it's not really an energy, it's energy that could be. But somebody said to me, all right, well, think of agoraphobia, your fear of heights, okay? You're standing on a high building, you're looking down, and you have that fear of heights, not because you're falling or anything, but there's the potential for falling, right? And that's the potential energy you have that you could be falling.
yes,
So your fear of heights is really sort of an emotional expression of potential energy.
I like that description.
I
But
thought that was fun.
yeah, potential energy is it's energy that's there. You just can't get to it really easily. It has to change.
You have to do something, yeah.
You have to do something to it. That's the way I think about potential energy.
Okay, what else, Grant?
Okay. When you're trying to make sense of something you observe, like say we come across a new phenomena or something that you're trying to understand, do you begin to see from a data perspective, like do you look at the observations that we have, or do you try to relate it to something physical? Do you try to look at it and relate it to an object or something like that?
Well, it's a good question.
The chat's been really good today.
That's a really great question. I would say that if to get it, for me, if I haven't done any observing in a long time, but I'm thinking back to my youth when I used to do that. When I would get some data, I would make sure first that what I'm seeing is got all of the systematic things that are related to the detector, things that are related to the instrument or the weather, like all of that I've already been able to take out. So when I look at the data, I try to say, okay, I expect that I should see this. Did I see that? Sometimes people expect to get some certain type of information because astronomers plan, especially if they use space telescopes, they have to have a really strong justification for why they want to use the Hubble Space Telescope or the future James Webb Space Telescope. So they have an expectation of what they might get. And so they're going to look to see if they got what they thought they were going to get. So that's definitely one thing. But the beauty of a science is that most of the time, there's many times when you're looking this way and something this way catches your eye that's unexpected. And so scientists have to be kind of looking in both directions, looking for what they're trying to study, but also look for the unexpected. So if I'm taking a picture of light in the visible, it might be that I expect this, but did I see any other features that I wasn't expecting? And that could tell me some physical process that's going on. If I'm using a model to explain the observations and they're not meshing together, then I have to sit down and say, hey, why is this not meshing? Is it my observations or is it the model? And so then you can tweak the model or say that or the observations weren't as good as they should be, and you need to take more data. So I would say there's both.
Okay. And Frank answered it a little bit online. But Frank, do you want to give your opinion on that, just because both of you are experts in your fields here?
Okay, well, my answer online was that, if you're looking at an observation, right, the first thing you want to do is try to figure out the physics that's going on there, right? Because if you're just doing the question was phrased in terms of numbers and equations, and the only equations you can use are the ones that relate to the physics that you think is going on there. I think there's a great time. It's a wonderful thing to look at something and realize, hey, I don't really understand what's going on here, because then there's more physics than you thought was involved. Like the Zeeman splitting of lines from the sun, which it just means that indicates that there's a really strong magnetic field on the surface of the sun, right? And you wouldn't expect to see these dual lines if you were just thinking in the normal plasma physics. But once you invoke these really strong magnetic fields, you go, ah, that's how you get this. And so it's, you know, it's good for a scientist to not know what he's talking about, because then that indicates there's something new to discover.
Always the context. You can understand anything if you have the understanding of the basic underlying principles or the context. I would approach it the same way Frank would. Understand what's happening there, and then from there you can build on what you have. Okay, so let's see. I asked online to see if we could get another good question.
There's one about, there was something about the Fermi bubbles. Yes.
Oh, yeah.
How did they measure the size of the Fermi bubbles of our galaxy?
Good catch, Frank.
This is not my area, so let me think about what they would have done.
Wasn't it quasar absorption line features?
I was going to say it would have to be something intervening for that. I know that feature, these bubbles that are blowing out of the galaxy, were not noticeable in the first several surveys at those gamma ray wavelengths. It was just recently, within the last couple of years or so, that they were able to look at the data, and they had hints that these bubbles were there because you can see them in the x-rays a little bit. And so there was an indication that something interesting was there in another wavelength in the x-rays. And so they looked at it in the gamma rays to see, is there something coordinating there? And so with really, this is going back to what I was saying, what do I know about the instrumentation and the observations, so that I can really push my data to its limits to know what's real and what's not real. And this feature is actually quite dim. It doesn't come out of the data easily. It's not like boom, pops in your eye like the emission nebulas that we were talking about.
That'd be way too easy.
That would be way too easy. I think you're right about the quasars, that we need to see some intervening material, because that gamma ray radiation is not, it's there, but it's not high intensity. There's not a lot of it there, I should say.
Okay, and I have one last one that is quick, but it's the one we'll end on here, which is, what is meant by a black hole being active?
Oh, okay, I have a good analogy for this one.
Bring it on.
This is my go-to analogy. Ready? All right. So I have a daughter. She's 3.5. So usually she's really calm, but sometimes if you give her too much candy, she might kind of get active. If you give her too much candy, she gets really active, and she might even throw things. She's very sweet though. But I have used this analogy in talks. So supermassive black holes exist. They need to become active, and usually they become active if they're fueled by infalling material. It could be debris that's around the supermassive black hole. It could be stars that orbits are decaying and falling into the supermassive black hole. So think of that as the candy, the sweets that get them fired up, right? And so if you can if you can fuel supermassive black hole, you can make it active. And how you find activity in a supermassive black hole depends on your wavelength of choice. So you could find them in the radio with those really beautiful giant jets that I showed you earlier. That's one way. Really close to the supermassive black hole, you can get some X-ray emission really, really close. And that's also indication of a supermassive black hole. You can also see there's some winds that come off of the disk. And so if you look in the UV, you can also get indication of some of that activity as well. Now our Milky Way is in a calm state right now.
Fingers crossed, by the way.
Yep.
You know. Yeah.
So there's my analogy for active supermassive black holes.
I'm sure your daughter appreciates being used as an analogy.
For black holes, no less. Later on, when she grows up, she'll find this video and you'll have some explaining to do.
That's right.
All right. So thank you, Quinn. That was a wonderful talk. Thank you, Grant, for taking care of the messages and such. Next month, September 1st, we will have Sailing Across the Local Universe with Ulysses, a Hubble program to observe ultraviolet light from young stars. The huge Ulysses program will be next September. If you were live, you would give a huge round of of applause for Quyen, so I'll give my virtual applause for Quyen. Thank you all, and have a great night.